Doctors, in this video we shall be discussing about conductance of electrolytic solution. So we very well know we have two types of substances. First are conductors and second are insulators. इन दोनों में basic difference क्या है कि conductors allow electricity to pass through them. इनसे electricity pass हो सकती है but insulators do not allow electricity to pass through them. Here electricity cannot pass. So conductors are basically of further two types. First type we have already discussed in previous classes. First type is electronic conductors, or we call them as metallic conductors. We all know metals are good conductors of electricity. Electronic or metallic conductors. All metals conduct electricity or they allow electricity to pass through them. So ऐसा metals में क्या होता है कि they allow electricity to pass through them? Conduction is mainly due to flow of electrons. Electrons flow, and with the flow of electron we call this current as electronic current, और इसका opposite we take the direction of current which is conventional current. So यहाँ पे electricity pass हो रही है लेकिन कोई decomposition नहीं हो रहा substance का. Electrons जो electricity है they are this is flowing due to the flow of electrons. So here conduction is due to flow of electrons and no decomposition is taking place. Second type of conductor is electrolytic conductor. Electrolytic conductors or electrolytes. Here यहाँ पे क्या होगा कि electricity pass करने की वजह से जो substance है NaCl, aqueous solution, this will decompose to form ions and then this will carry on the charge. This will carry forward the charge. So यहाँ पे the conduction of electricity or the flow of electricity is due to the flow of ions, and here the flow of electricity is due to flow of electrons. So this is the basic difference between electronic and electrolytic conductors. Here no decomposition is taking place, whereas here decomposition of the electrolyte takes place and ions carry forward the charge. So यहाँ पे क्या होगा, electrolytes are further of two types. एक जिनमें complete dissociation होगी, we call them as strong electrolyte, and second जिनमें dissociation 5% से कम होगी, they are weak electrolytes. Strong electrolytes के example है हाइड्रोक्लोरिक एसिड, नाइट्रिक एसिड, सल्फ्यूरिक एसिड और कुछ बेसिस भी हैं, सोडियम हाइड्रोक्साइड, पोटेशियम हाइड्रोक्साइड. वीक इलेक्ट्रोलाइट्स के सबसे फेमस एग्जाम्पल है एसिटिक एसिड, देन वी हैव हाइड्रोजन साइनाइड, कार्बोनिक एसिड, फॉस्फोरिक एसिड, अमोनियम हाइड्रोक्साइड, कैल्शियम हाइड्रोक्साइड एंड एल्यूमिनियम हाइड्रोक्साइड. सो यहाँ पे जो डिसोसिएशन होती है ऑलमोस्ट 100% या 90% के अराउंड होती है, लेकिन यहाँ पे जो डिग्री ऑफ डिसोसिएशन है दिस इज लेस देन 5%. 5% से भी कम एसिड टूटेगा, देन दैट विल बी वीक इलेक्ट्रोलाइट. और यहाँ पे जो इलेक्ट्रिसिटी कंडक्ट होगी दिस विल बी कंडक्टेड टू अ लार्ज एक्सटेंट, वेयर हेयर इलेक्ट्रिसिटी विल बी कंडक्टेड टू अ स्मॉल एक्सटेंट. Conductors allow electricity to pass through them and insulators do not allow electricity to pass through them. Conductors are of two types, electronic and electrolytic. Electronic conductors conduct electricity without undergoing decomposition, and conduction is due to flow of electrons in them. For example, all the metals. Some non-metal like graphite and some minerals also conduct electricity due to flow of electrons. Next is electrolytic conductors, aqueous solution of acid, bases and salts. Here it undergoes dissociation or decomposition when current is passed through them, and conduction is due to those dissociated ions or flow of ions. Solution of acid, bases and salts in water are example of electrolytic conductors, and it may be strong or weak. Strong electrolyte when decomposition or dissociation is complete, almost 100%, it is almost complete, and weak when degree of dissociation or decomposition is less than 5%. So strong electrolyte when dissociate almost completely in aqueous solution or in molten state, and they conduct electricity to large extent, and for example hydrochloric acid, nitric acid, sulfuric acid, sodium hydroxide and potassium hydroxide. Weak electrolyte dissociation is less than 5%. They have very low degree of dissociation and they conduct electricity to small extent. Acetic acid, hydrogen cyanide, carbonic acid, phosphoric acid, ammonium hydroxide, calcium hydroxide and aluminium hydroxide. So we have two type of conductors, metallic and electrolytic. In metallic conductors, the flow of electricity takes place without decomposition of substance. Substance is not decomposed. Whereas in electrolytic conductors, the aqueous solution of that substance, electrolyte, is decomposed to form ions, and then flow of ions will facilitate the flow of electric current. So this is electrolytic conductor. Here it is due to flow of ions and here it is due to flow of electrons. Now what happens if we increase temperature in both the cases? यहाँ पर temperature increase करने पर generally kernels are there. Kernels are what? If a substance is losing electron, So the positive charge which is left, we call this as kernel. So kernels के electrons के flow होने की वजह से ions flow कर रहे हैं. Now what happens when we are increasing the temperature? Then kernels will start vibrating. जब kernels vibrate करेंगे तो electrons उतना effectively flow नहीं कर पाएंगे, तो temperature increase करने की वजह से resistance भी यहाँ पर increase करेगा. Whereas in case of electrolytic conductors, अगर हम temperature increase करेंगे तो यहाँ पे NaCl और भी ज्यादा डिकम्पोज होगा, डिकम्पोजिशन विल बी मोर, सो इन दैट केस रेजिस्टेंस विल डिक्रीज. Metallic conductors, conduction decreases with an increase of temperature. Why? Because kernel will start vibrating and this will hinder the flow of electrons. And in electrolytic conductors, as we are increasing temperature, so the electrolyte will decompose more or dissociate more to give more ions, and this ions will facilitate the flow of current. Next is resistance is offered due to vibrating kernel, and here the resistance is offered due to viscosity of solvent, the interaction between the layer of solvent, or interactions like solute-solute interaction which is between the two solute, for example Na positive and Cl negative. इसके बीच में जो इंट्रैक्शंस होंगी, दिस इज प्रोड्यूसिंग हिंड्रेंस टू फ्लो ऑफ आयंस और फ्लो ऑफ करंट. नाउ व्हाट इफ अगर हमने इसमें टेम्परेचर इंक्रीज कर दिया, दे विल सेपरेट आउट and as a result flow of ions will be more, so flow of current will be more. Solute solvent interaction, like this is solute, this is surrounded by solvent molecule, so there is an interaction between both of these. This is known as solute solvent interaction, and third one is solvent solvent interaction. So all of these things contribute to resistance. If all these things अगर हम इनको remove कर दें, there will be increase in conduction. Factors affecting metallic conductance are nature of metal and the structure of metal, how many electrons the metal can provide, number of valence electrons per atom, and the temperature. We very well know with increase in temperature the conduction decreases because kernels start vibrating. Factors affecting electrolytic conductance. First is nature of electrolyte. We very well know strong electrolyte completely ionize हो जाते हैं, so they conduct electricity to larger extent, whereas weak electrolyte ionize to small extent, so they will conduct electricity to small extent. Next is nature of solvent. What nature the solvent are having? Either they can be polar or they can be non-polar. So electrolyte will ionize more in polar solvent like water, and greater will be the polarity, greater will be the conductance. Next is size of ions and solvation. Greater the size of ion, greater will be solvation. आयन का साइज जितना ज्यादा होगा उतना ही ज्यादा इसके अराउंड वाटर मॉलिक्यूल्स आएंगे, एंड सल्यूट सॉल्वेंट इंट्रैक्शन बढ़ गई तो इसकी वजह से दिस विल हिंडर देयर फ्लो, सो दिस विल डिक्रीज कंडक्शन. नेक्स्ट इज कंसंट्रेशन ऑफ सोल्यूशन. हायर द कंसंट्रेशन, लेस इज द कंडक्शन. क्योंकि कंसंट्रेशन ज्यादा होने की वजह से आयन ज्यादा पास होंगे, सो दे विल नॉट मूव. सल्यूट इंट्रैक्शन विल बी ग्रेटर, सो दे विल नॉट फ्लो इफेक्टिवली. नेक्स्ट इज टेम्परेचर. वी वेरी वेल नो विद इंक्रीज इन टेम्परेचर द interionic attractions decreases. Solute interaction, solute solvent, these interactions decreases, so as a result conduction will increase. Resistance is the obstruction to the flow of current. In case of metallic conductors, the flow of electrons, obstruction to flow of electrons, and in case of electrolytic conductance, obstruction to the flow of ions, and its unit is ohm and symbol is this. Now what happens? Resistance, if we are drawing a cell like this, an electrolytic cell where two electrodes have an area A and the length or the distance between these two electrodes is L. They are dipped in a solution. So now what we are having? We have area of cross section A, length which is L. Now resistance is directly proportional to the length of the conductor. More will be the distance between this, more will be the resistance, and it is inversely proportional to क्रॉस सेक्शनल एरिया. पतले वाले के लिए एरिया जो होगा वो कम होगा, दैट मीन्स रेजिस्टेंस विल बी मोर. लेकिन अगर वायर मोटी होगी, इलेक्ट्रोड मोटा होगा, तो एरिया जो है वो ज्यादा होगा एंड रेजिस्टेंस विल बी लेसर. सो रेजिस्टेंस इज डायरेक्टली प्रोपोर्शनल टू लेंथ बट इनवर्सली प्रोपोर्शनल टू ए. इफ वी कंबाइन बोथ ऑफ दीज विल बी गेटिंग आर इज डायरेक्टली प्रोपोर्शनल टू एल अपॉन ए. प्रोपोर्शनैलिटी को इक्वालिटी में कन्वर्ट करना है, वी हैव टू यूज ए कांस्टेंट, एंड दैट कांस्टेंट इज रो. So resistance is equal to rho L by A. R is resistance, L is length or distance between these two electrodes. Length in case of metallic conductor, and in case of electrolytic conductor it is distance between two electrodes. A is cross sectional area of these two electrodes, and rho is specific resistance or resistivity. Now what if we have to write the definition of specific resistance or resistivity? So this value is equal to resistance. R is equal to resistance when L is 1 centimeter. That means the distance between two electrodes is 1 centimeter and cross-sectional area of both these electrodes is 1 centimeter square. Then specific resistance is the resistance. Resistance is equal to the specific resistance or resistivity. We are considering this for a solution like this solution. Here length is 1 centimeter and if area is 1 centimeter square. So this is the volume. Volume is what? Volume is length into area. So if length is 1 centimeter and area is 1 centimeter square, so volume is 1 centimeter cube. So इस volume में कितने ions है that are their resistance is known as specific resistance. The resistance offered by all the ions in 1 centimeter cube of a solution is known as specific resistance. Resistance offered to all the ions of an electrolyte which are present in 1 ml solution. So volume is A into L. So when area is 1 centimeter square, L is 1 centimeter, so volume is 1 centimeter cube. Resistance offered by or offered to all the ions in 1 centimeter cube or 1 milliliter ions in solution. Resistance की unit होती है ohm. Now we have to find out unit of resistivity. We very well know R is rho L by A. So the formula of rho is R A divided by L. This will be the formula for resistivity or specific resistance. Since unit of rho R is ohm and for A it is centimeter square and for L it is centimeter, this and this will get cancelled. So unit will be ohm centimeter or ohm meter if area and length are in meter. But generally we use this ohm centimeter. So we have conductance. Conductance is the ease with which the current flows. Now current is due to flow of electron or ion. So ease with which electrons or ions flow. Its unit is mho or Siemens. Now G is 1 upon R. We very well know R is rho L by A. So it is 1 by rho A by L. And 1 by rho we call this constant as new constant which is kappa. Kappa is specific conductivity. A is cross-sectional area and L is the distance between the electrodes if we are talking about electrolytic conductors. So is cross-sectional area. So here kappa is specific conductance or conductivity, and kappa will be equal to conductance when the cross-sectional area is 1 centimeter square and when the distance between the electrodes is 1 centimeter. Or we can say since volume is equal to area into length, so volume is also 1 centimeter, area is also 1 centimeter square, distance is also 1 centimeter, so volume is 1 centimeter cube. So we can also say specific conductance is the conductivity of 1 centimeter cube of the solution or 1 milliliter of the solution. So conductance due to all the ions of 1 milliliter of solution, we call this as specific conductance or conductivity. Conductance due to all the ions of an electrolyte present in 1 ml solution is specific conductance or conductivity. Now what about units? Here we have to find kappa. G, L here is divide, वहाँ पे multiply and G L by A. This will be the value of kappa. Now unit of conductance is Siemens or mho, whatever you can write. If we are writing it in terms of Siemens, so this will be Siemens. Value unit of L is centimeter, whereas unit of area is centimeter square. Centimeter and centimeter square will get cancelled. So unit of conductance is Siemens per centimeter or Siemens per meter. This is the SI unit. Constant G star. If we are taking an electrolytic cell and here two electrodes are there The distance between these two electrodes is L and the cross-sectional area of both of these electrodes A. They are dipped in electrolytic solution which may be of their own or water or anything. Electrolytic solution में dipped है. So the ratio of the distance between two electrodes divided by cross-sectional area is known as cell constant. Cell constant is the ratio of distance between electrode divided by area of cross-section of electrode. G star is equal to L by A. So we can modify this formula of specific conductance or conductivity where kappa is G into L by A and L by A is cell constant. So kappa is equal to G conductance into G star which is cell constant. Now talking about unit, we very well know the unit of length is in centimeter and unit of area is centimeter square. Basis same है, divide में, so power will get subtracted. So answer will be centimeter inverse. This will be the unit of cell constant and SI unit will be meter inverse. Now there are two more kind of conductivities. First is molar conductivity. नाम से ही पता चल रहा है 1 mole of electrolyte जितने वॉल्यूम में होगा 1 mole of electrolyte जितने वॉल्यूम में होगा उतने वॉल्यूम की ions की conductance is known as molar conductivity. So conductance due to all the ions of that volume of electrolyte which contains 1 mole of electrolyte. So what we do to write the formula of this? So lambda m is equal to, this value is kappa, specific conductivity, which is the conductance due to all the ions in 1 milliliter of solution multiplied by volume. Because here volume is not 1 milliliter but volume which contains 1 mole of electrolyte. So this is the formula of molar conductivity. Now what if we have to write it in terms of molarity? We very well know that molarity is number of moles upon volume of solution. So number of moles we already wrote, 1 mole should be there. So molarity is equal to 1 upon V, which implies that volume is equal to 1 upon M. Volume is in liter. What if we are writing volume in milliliter? 1 liter में कितने milliliter होते हैं? 1000. So we have to multiply this by 1000. So volume in milliliter will be 1000 upon M. M is molarity. So here we'll write this. Molar conductivity is kappa into volume की जगह we'll write 1000 upon molarity. 1000 upon molarity. So this will be the formula for molar conductivity when volume is in milliliter, and molarity we have to write here. Kappa is specific conductivity. Here kappa is specific conductivity and volume is in liters. Now what are the units of molar conductivity? We very well know the unit of kappa is Siemen or mho, and unit of molarity is how much? Mole per liter. Here we have written volume in milliliter, so we will be writing mole per centimeter cube. And the unit of kappa is not Siemen but Siemen per centimeter. That we have written in previous section, Siemen per centimeter. So that we will be writing as Siemen per centimeter, mole per centimeter cube. Now अगर हम दोनों को ऊपर ट्रांसपोज कर दें, Siemen centimeter cube, बेसिस सेम है, डिवाइड में पावर सब्ट्रैक्ट हो जाएंगी, माइनस माइनस इज +3, ये ऊपर चला जाएगा, दिस विल बी मोल इनवर्स, प्लस माइनस इज माइनस, सो सेंटीमीटर स्क्वायर mole inverse. This will be the unit for molar conductivity. Siemen centimeter square and mole inverse. And we can also write this in meter square, but that will be in SI unit. Siemen meter square per mole. That will be the SI unit. Equivalent conductivity. Conductance due to all the ions of that volume of electrolyte which contains 1 gram equivalent of electrolyte. So this much volume we require, and this much volume, the conductivity of this much volume will be equivalent conductivity, and the formula will be equivalent conductivity is equal to kappa into volume. Now volume in which 1 gram equivalent of electrolyte are present. Now normality we very well know, this is gram equivalent upon volume of solution. Now we have written gram equivalent equal to 1. For 1 gram equivalent, we are calculating the conductivity. So it is 1. So normality will be equal to 1 upon volume. So volume will be equal to 1 upon normality. This is volume in liters. Now what if we have to write volume in milliliter? 1 liter में 1000 milliliter होते हैं. We have to multiply this by 1000. So this will be in terms of milliliter. When volume is in milliliter, the equivalent conductivity will be equal to kappa into 1000 upon normality. This will be the formula for equivalent conductivity. where kappa is specific conductivity, N is normality, and here V is volume. This volume is in liters, but when we are writing it here, we'll take this as this in milliliter. Units of this will be, we very well know the unit of kappa is Siemens per centimeter, and the unit of normality is equivalent. We are taking this in normality is what? Normality is gram equivalent upon volume. Gram equivalent is an equivalent divided by, sorry if we are writing this here, volume is in centimeter cube. So per centimeter cube. This will be the unit of normality and this will be the unit of kappa. Now अगर हम इसको ऊपर ले जाएं, साइमन सेंटीमीटर इनवर्स, ये डिवाइड में पावर सब्ट्रैक्ट हो जाएंगी, माइनस माइनस इज +3, इक्विवेलेंट को ऊपर ले जाएं, दिस इज -1, प्लस माइनस इज माइनस, सीमन सेंटीमीटर स्क्वायर per equivalent. This will be the unit, and in SI unit will be Siemens per meter square per, Siemens meter square per equivalent. What is the relationship between molar conductivity and equivalent conductivity? Molar conductivity is kappa, specific conductivity multiplied by 1000 upon molarity, whereas equivalent conductivity is kappa multiplied by 1000 upon normality. So if we divide both of this, kappa into 1000 and kappa into 1000 will get cancelled, normality upon molarity. Normality is number of gram equivalent upon volume, and molarity is number of moles upon volume. Volume and volume will get cancelled, and number of gram equivalent is mass upon equivalent mass, and moles is mass upon molar mass. Mass and mass will get cancelled, molar mass upon equivalent mass. Now equivalent mass is molar mass upon n factor, molar mass and molar mass will get cancelled. That means molar conductivity upon equivalent conductivity is equal to n factor, where n factor is the number of ionizable ions, either H positive or OH negative. For example, in case of HCl, number of ionizable H positive is 1. In case of H2SO4, number of ionizable H positive is 2. Whereas in case of H3PO4, number of ionizable H positive is 3. And in case of NaOH, number of ionizable OH negative is 1. In case of BeOH2, it is 2. And in case of AlOH whole thrice, it is 3. So now summing up, we have discussed overall 6 physical quantities. First one was resistance, whose value is R is equal to rho L by A, where rho is resistivity, L is distance between the electrodes, and A is cross-sectional area of electrode. Commonly used and SI unit both are ohm. And then we have conductance. Conductance is denoted by symbol G, and it is equal to kappa into A by L. Resistance is the obstruction to the flow of current, whereas conductance is the ease with which the current flows, and its unit is ohm inverse, because since here it is 1 by R. So this value will be ohm inverse, or its SI unit is Siemens. Next is conductivity. Conductivity is denoted by kappa. Conductivity is nothing but equal to G into L by A, where G is conductance and L by A, L is the distance between conductor, and A is cross-sectional area. If we are considering this for an electrolyte, so L into A is what? L into A is volume. So 1 milliliter volume is conducting how much of electricity? We call that conductance as conductivity. So conductance of 1 milliliter of volume of electrolyte is conductivity, and its unit is ohm inverse, centimeter inverse, and SI unit is Siemens per meter. Next is cell constant, L by A, where L is the distance between electrodes and A is the cross-sectional area. So it is the ratio between L and A, and its unit is centimeter inverse and SI unit is meter inverse. Next is molar conductivity. Molar conductivity is how much 1 mole of electrolyte is conducting electricity. If we have 1 mole of electrolyte, so volume in which 1 mole of electrolyte is there, and the conductance of this much volume is known as molar conductivity. And its formula is kappa into 1000 upon m, where kappa is conductivity, m is molarity, and its unit will be ohm inverse centimeter square per mole, or Siemens meter square per mole. Next is equivalent conductivity. So the conductance of that much volume which contains 1 gram equivalent of an electrolyte, that conductance is known as equivalent conductivity, and its value is kappa into volume, or kappa into 1000 upon normality, where its commercially used unit is ohm inverse centimeter square per equivalent, and SI unit is Siemens meter square per equivalent. Molar conductivity, we have to find out the molar conductivity of a 0.5 mole per decimeter cube. Molarity is given as 0.5 mole per decimeter cube, that means mole per liter. Solution of AgNO3 with electrolytic conductivity, that means kappa 5.76 into 10 raised to the power minus 3 Siemens per centimeter. So in formula, we write molar conductivity is equal to kappa in Siemens per centimeter, 5.76 into 10 raised to the power minus 3 divided by molarity in mole per liter, 0.5. Now here we have written centimeter. So why this is per liter? So that is why we have divided by this by 1000. That is the main reason why, because we take molarity in mole per liter, but kappa is in centimeter. So that is why we divide this by 1000 to get the value, overall value in centimeter. Now what if we solve this? This and this will get cancelled. Because this is 10 raised to the power minus 3 and this is 10 raised to the power 3. Bases are same, power will get added. So minus 3 plus 3 is 0. Anything raised to power 0 is 1. So this value, if we solve this, we will be getting 11.52, which is given in option B. Specific conductance of 0.1 normal KCl solution, kappa is given as 0.012 ohm inverse and centimeter inverse. Resistance of the cell containing the solution at same temperature was found out to be 55 ohm. If resistance is this, so conductance is 1 by R. So conductance will be 1 by 55 ohm inverse or Siemens. Now we very well know conductivity is equal to conductance into cell constant. We have to find cell constant. So cell constant will be equal to G यहाँ पे multiply, वहाँ पे जाके divide हो जाएगा, kappa upon G. Kappa is 0.012 divided by G. G it is 1 upon 55. 55 यहाँ पे divide है, ऊपर भेजेंगे multiply हो जाएगा 0.012 multiplied by 55. We'll get the answer if we multiply this. So answer is 0.66 centimeter inverse, which is given in option B. On heating one end of a piece of metal, the other end becomes hot. If we are heating this end also becomes hot. Why? Because in metal the conduction is due to the flow of electron. So यहाँ पे an energized electron will move to this place, so and the electron will move from this. So all the electrons will get heated by this. So the option will be option first, energized electrons moving to the other end.